Hmm.
Hello everyone, welcome back to our YouTube channel, Becoming a Rust Developer. I'm Desire and today we've got Ako who has just completed the course Linux Basics for Robotics and she will be giving us a presentation on that. So let me hand over the platform to her so that she can begin her presentation. Alright, whenever you're ready, Ako.
All right. Okay. Hello, everyone. So we're just going to begin with a live demonstration of the project on the Rust 2, sorry, on the fast bot robots. Currently, it's hiding. It's hiding in in the corner of the screen, and the joystick is
um,
not moving it.
okay,
So I'm going to try the code to see if that would.
try using Teleop to get it. You know Teleop, right?
Okay. Yes.
Okay, so
Mm.
try roast to run teleop twist keyboard, teleop twist keyboard, and then let's see if it can respond to that.
It still doesn't seem.
Okay.
Wait. Let me connect to the robot interface. Maybe that's the problem.
No, not really. It shouldn't be happening. So, in your second tab now, can you type roast to topic list? Let's just see if we're really connected. Okay, we should be connected. Okay, and there is. Okay, scroll up a bit. Let me check if we've. No, in the second terminal, the one below that.
Okay.
Yeah. Okay, alright, so just disconnect and reconnect again. I think that might be the way to solve it. So
Okay, then I'm glad we are starting with the live demo.
yeah, yeah, that's the main reason why we have to do it.
Alright.
Alright, try using the joystick one more time. Still no response.
No, it's still not responding.
Okay, hang on one sec.
Good.
Alright, okay, let's continue, Ako. So you can start your demo.
Okay, so I'm just coming to run the different programs.
Alright.
Mm. So right now it's running the naive obstacle avoider with bash scripts. And then let me run the robot statistics so we see the status of the robots as it navigates.
Okay.
As you see, there's no obstacle, so that's why it's just moving forward, but immediately it comes within 3 meters of an obstacle. It uses the logic that I implemented to either turn left or turn right, depending on which area is more free.
Okay, okay.
Yeah. Okay.
Alright,
So this shows that it's working on the actual robot. So let me go over to my presentation.
why did it have to rotate a full 360 degrees? Anyway, yeah, so I'm trying to understand. Maybe it's just lag, but yes,
Mhm.
what's going on there? Is this typical behavior, or this is something else that you've not seen before?
It's not actually typical behavior. It's supposed to rotate
A certain
for a
amount.
few seconds. Yeah, it's not supposed to
Okay. So
go.
no worries. I think I think I know what's going on there. So just stop the script that's running at the moment, the obstacle avoider,
Okay.
and then your logs are saying that it's supposed to be going forward, right? Okay. Yeah. So there's
Go
something going
forward.
on with the
Yeah.
hardware. Yes. Okay. Uh, so just stop everything, and then we can go on to the presentation and see, and you can start explaining.
Okay. This is the very interesting part of our robotics. Okay, let me start my presentation.
All right.
So this is the link for robotics representation and presentation. And this is for my certification at the construct. And presenting will be me, Ako Ayo Oku.
Mm-hmm.
So the problem is a naive obstacle avoidance problem where we use a planar laser rangefinder to detect obstacles and then adjust the robot's movement according to the threshold.
Mm-hmm.
It can either move forward, turn left, or turn right to find a safe path.
Mm-hmm.
The text that we used was Linux bash scripting for executing the obstacle avoidance logic and the various algorithms. We used Rust2 as the middleware framework for routing data across the network. And then we used the robot interface as the abstraction layer for translating our commands to the physical motors and the sensors on the robots.
Mm-hmm.
So for the inputs, we needed 5 ray indices from the laser scanner array. So that's from the robot LiDAR. We needed its left laser ray, the front left laser ray, the front laser ray, front right, and then the right laser ray. And then the output, we had 3 velocity commands, which was, like I said previously, to either turn left, move forward, or turn right.
Mm-hmm.
And this is how they were represented in the various code files. So for the logic and the process, we had a threshold of 3 meters, and how the evaluation process was is if any of the laser scanners were within that 3 meter threshold, so if they were less than the threshold, then that means that there's an obstacle detected and the path is not free, and so that will be evaluated to 0. So 0 in this case signifies that there's an obstacle detected, whereas 1 means that there's no obstacle detected, so there's a free path and you can move in that direction.
Mm-hmm.
This was all done in the obstacle avoider.bash script. And so how I thought of it was as a truth table with 8 cases,
Mm-hmm.
where the main things that we needed to evaluate were the front laser rays, and depending on the front laser rays, we'll be able to.
Hi, Akok. Can you hear me?
Intended outputs. So
Okay.
if robots, and so we need to evaluate whether there is going left or right.
Mm-hmm.
Whereas if the right side is free, meaning that means 1, then you turn right. If the front scan is free, move forward. If the front and left, so the left side of the robot is free, turn right, and so on and so forth. And so that's how I was able to evaluate the truth table. And the files that I created and implemented code in was the robot functions.bash file, which contains the various setter and getter functions from the sensor and motor readings.
Mm-hmm.
The obstacle avoider.bash, which implements the truth table logic that I showed earlier to avoid obstacles in the robot's path. And then the robot statistics, which monitors the status of the robot's ODOM readings as it navigates its environment.
Mm-hmm.
I think the only challenge I faced in the robot statistics, the bash script, it said that we should print IMU angular velocity and IMU linear acceleration. But then when I went to the robot functions, the bash, there wasn't any function specifically for the IMU. And so then I inspected the robot interface .py file, and I saw that there were comments that said that the fastbot does not have an IMU. So I just figured that there's no IMU readings.
Mm-hmm.
So I left it blank.
Yeah. A good way of
Then
learning
for lessons,
this.
Then for lessons learned, I've not really done bash scripting before, so I learned about the awk text processing tool, which extracts data. So it's so how the left side of this command works is that it gets the value as a string text from the parameter, the ROS2 parameter, um, ROS2 parameter, yeah, from the ROS2 parameter, let's say thingy,
Parameter
right?
list, yep.
And it's double value is 0.45. But what we actually need is that 0.45 character, not the whole string text. So what the awk does is that it will extract the fourth argument. So that's why it says $4 from the string text. So we only get the 0.45 value.
And on
Then
what basis does it separate? Does it separate the different?
It's separated by the spaces. So the double is one character, value is one character, is one, and then 0.45. So based on the spaces in them.
Wonderful. Okay.
Then to set a parameter, to set a parameter, it takes the first argument from after you've called the function. So the set cmd val function, the first argument after that is what it sends through ROS to the robot interface to set a parameter. So then I also learned bash scripting for robotics. I learned that I think bash scripting can only handle integer calculation. So you need a command line calculator to enable floating point precision. So that's what that BC minus L does. It just allows it to handle floating point numbers, which is what the LiDAR gives you. That's the output of the LiDAR, the floating point values.
Yeah.
And then the last one is I was a computer science graduate, so the fact that I had to repeat a lot of code was annoying me. So I decided to put the various outputs into functions, like the turn left, turn right, and then move forward into functions. So when I'm writing the actual code, then for each case, I just tell it to turn left. Like I just call the function, and it's easier for me to. It's a lot less code. And then the resource I use was Geeks for Geeks because I didn't know how to do that in Bash. Then the demo, and this was the robot in simulation, which was working perfectly well. And then the real robot was also working perfectly well. It's my fault. I didn't beforehand before the presentation. I tested a long time ago because I had done this a long time ago.
Yeah, no worries. So, I think it's still important that you got a copy of that. Even though we did a live demo, this is still very much a prerequisite to a worthy presentation. So that's good.
Okay, thank you. Yeah, so from here, it wasn't turning, like, it wasn't spinning the whole 360.
Yeah, that one is an issue with the robot, so you don't have to worry about it.
Okay. All right. Yeah. So it's a reactive algorithm, which was also like,
and okay, so
annoying me because
there are a couple of interesting things. So what I want to know is, how did you determine how much your robot has to turn, right? Because different people do it differently. I want to know, what was your criteria? Did you have anything in mind, or as long as it avoided an obstacle, you were fine with it?
Oh no, I think I was just following instructions. So I know that what I used the exact same value that I saw in the project.
Yeah.
I didn't change because it was annoying me that it was turning too much. It was turning a lot more than I wanted to turn.
Yes, so part of my reason for asking is that these values, they're given to you as examples. You can surely make them better if you can, and we highly encourage that you do that. So, but no worries. I'm just trying to see if you had a test for yourself, and did you discover any of the things that you thought were constraining, which this one being one of them. Actually, we don't hold you to that value. We want it to perform well. That's the most important thing, right? But yeah, it's all right. I'm glad you also noticed that it was doing things beyond what you expected it to do. So it's up to you to make it better.
Okay. I think going forward, I'll put that in mind, because I'll just I want it to be, follow the instructions. I'm a very follow the instructions type of person.
Yeah, it's
So that's good
understandable.
to
It's understandable. So let's
know.
try go to the real robot one more time and maybe try move it in a different manner. And I'm hoping we get a different outcome this time around. But
So should I run the
mhm,
script again?
I think maybe
Okay.
teleoperate it out of that position just to make sure we don't get stuck with the same glitch.
Oh, it's the same thing. I was making.
Um, yeah.
Okay, so let's start from here.
Yep.
Okay. Okay, I think it's working much better.
Yes, but I can still see some subtle issues there. Anyway, so
Yeah,
did you implement the reverse mechanism or it just happened?
I think it just happened. I didn't implement any reverse mechanism.
Okay, all right. Yeah, that's why I'm saying there are still some issues. But anyway, thank you very much for your wonderful presentation, Ako, and for making the effort to put it in the slides and making them as clear as possible. Very, very well done on that part. And we would like to conclude here. So wonderful. Just hang on and we'll finish
Okay, thank you too. This was actually a fun project.
all right, everyone. So a warm congratulations to Arco and for a job well done. We'd like to encourage all those of you who would want to try out this course. This is basically a prerequisite to most of the stuff that you will do with our courses. So go ahead and try it for yourself. Prepare the presentation, and then you can also come and showcase your work. So until next time, keep pushing your Roche learning. Bye bye.